Hi everyone, and thanks in advance for your participation. The goal of our activities is to teach the basics of quantum programming with the help of a game we created called the two-qubit dance. This game resembles Just Dance, but ours integrates a good amount of scientific content. While the game is fun to play in itself, it's even better to understand the science behind it, so the participants need a bit of theory, which include understanding how the quantum computers work, which is entirely different from how classical computers, like the ones we use in our everyday life, how those work. So the series of activity introduces some basic knowledge about how classical computers and binary codes work, because speaking of zeros and ones can be very abstract. And after that, we can add notions about quantum physics. All this together makes quantum computing understandable so the students can enjoy the game and see their new knowledge at play. Teachers have very few preparations to do for this series of activities, mostly making sure that you familiarize yourself with the content beforehand. You will have an overview of everything and some explanations in the teacher's guide, but you will also have access to a ready to use PowerPoint presentation where everything is explained in the presenter's note. As you can see in those notes, you'll find that the actions and instructions for the teacher are in italic, and the suggested speech or explanations to give to the class are in bold. But of course, feel free to change anything to your liking. I recommend having the PowerPoint open when reading the teacher's guide. That way, you will be able to switch from one another when you feel that you need more details. Everything you need to know is explained in details in the presenter's note in the PowerPoint, but for a quick overview of the theory, you have to know quantum computing is entirely different from classical computing because the hardware is different and uses quantum properties, while classical computers don't and actually can't. Those properties include the superposition of states, which is where different information is encoded by the same electronic piece of the hardware, the physical qubit. Its name comes from quantum bit. This means that the qubits can process many information at the same time, which is why quantum computers are so efficient for certain types of problems. Quantum algorithms are programmed through the use of quantum logic gates, which affect the qubit states in specific manners. The qubit can be represented by a geometrical tool called the block sphere. That's a 3D representation where an arrow points from the center straight to the surface of the sphere, and its position corresponds to the state of the qubit, with up being the zero state and down being the one state. The three activities are incorporated in the presentation, so you'll know when it's time to do each one. The first two activities focus on binary code as used in classical computers, where you only have 0 or 1, and you use this binary code to compute more complex information and operations. With the first activity, the students familiarize themselves with having pairs of answers used with their literal meaning of yes or no, 0 or 1, with a convention based on how you point at them, left and right, up and down. My answer cards are a bit small, but you should make them big enough so that the whole class can see them. Ask questions that you think would be funny or that the students can relate to. Ask a few one with the yes no pair, left and right. Then switch to up and down. Then keep up and down, but now with the 0 1 pair of cards. The students won't know it yet, but we end with the convention that we'll keep using for the rest of the activities, where up means 0 and down means 1, because this is the convention used with the block sphere to represent the qubits. For the second activity, we use this convention, but this time we add a level of abstraction where we combine the zeros and ones to form letters in ASCII code to communicate with them. You first show the students how to use the code by making them guess a letter using your arm to point up and down. Then you make them guess a word with a series of arrows displayed on the PowerPoint that we also included in their student sheets. Then you let the students try it on their own in pairs, where one student sorts a word and communicates it by pointing up and down, and the other students write the signals and translates them to find a word. Then they switch roles and repeat the activity for a few words. Note that we included a page with encoded three-letter words that you can print and cut, but you can also prepare different or longer words if you'd like. The final activity is the two-qubit dance at last. So this game consists of two videos, the tutorial and the actual game with a higher level of difficulty and the surprise addition of a second player.
Of course, even though the players feel the impulse to go through the motions to the best of their capacities, those are not interactive video games, so there won't be a score or anything giving them feedback. The game consists simply of videos, so you can access them easily without the need for special equipment to play it, and there's no limit to the number of players.
Before starting the video, make the students spread across the room in order that they have room to move their extended arms without touching anyone else. In the tutorial, you first have a visual representation of the Bloch sphere and the effect of quantum logic gates applied to it. Then the choreography starts and we do those movements with our right arm. It helps to instruct the class to follow the dancing character as if they were looking at themselves in a mirror. The difficulty increases gradually in the tutorial with increasing speed, but also with the addition of the other arm, meaning each person can make a two-qubit dance. When the tutorial finishes, make the students go back to their desks so you can make them notice with the help of the PowerPoint how the dance integrated some important notions that you had presented earlier. Once that's done, they can spread themselves again in the classroom to do the second video, the actual game, with a higher difficulty level and with the surprise addition of a second player. You can warn them about it in advance, or you can let them be surprised by it and only instruct them how to deal with it when it happens. You can either tell them to dance in pair with the person next to them, or you can instruct each side of the class to follow the character on their side. This second option is easier, but it can also be fun to interact with one specific person as a pair, so the choice is up to you. After the dance, as an optional extension of the activity, you can also show students the video clip we released at the same time as the game. It was filmed at different sites of the quantum ecosystem we have here in Sherbrooke in the Canadian province of Quebec. And we had so much fun having people from our whole community play the game. There were students, teachers, startup employees, big company employees, our technicians, and more. Oh, and we even got the permission to film beside the IBM's quantum computer in Bromont. So it's a nice glimpse of some people and installations from the quantum science world of today. And if your students would like to push it further and program actual algorithms that could be run on a quantum computer, you can do so with the Quantum Enigmas and the Skills Build free educational activities that we made in collaboration with IBM. We left those links in the guide. And that's it. Thanks again, and don't hesitate to leave lots of comments to help us improve our part of the APS Quantum Kit.